Alright, so this is the first lesson that I'll be presenting solely through the video. It's 5:01. It's Friday, and I'm still at school. So, today I'm going to be talking about inverse trig. Inverse trig, as you might be able to tell, requires some knowledge of trig. If you want to wait to watch this until after Wednesday, Thursday, Friday next week, you will know substantially more trig than you might know now. Otherwise, you might want to pause this video, get a unit circle, look at notes, brush up on trig in some way, because it's going to be a bumpy ride if you don't understand what sine, cosine, and tangent are. So, I hope for all these videos to be about a half hour. The reason I can do an hour-long lecture in a half hour is because nobody's asking questions. Make sure you come and ask questions. Make sure you still take this class seriously. Without further ado, what I meant was make sure you take the BC test seriously and don't just assume that watching these videos has prepared you. If you are watching these videos and not doing the homework, you are going to fail the BC test miserably. Now, 6.2 is a lesson that we will do in AB. However, what I will be doing in 6.3, 6.4, 6.5, everything after this will depend on this knowledge. This is an inverse trig function. We call it arc sine. We call it arc sine. You may be familiar with it in this term. Y equals sine inverse. With that -1 exponent looking very tantalizing. The reason that that is awful notation, that we all know it's an awful notation, is because you all know, oh, -1 exponent, I know what that does. Well, some of you do. 1 over sine x. Now that is not the same. Those two things are not the same, and that's why I much prefer the arc sine notation. The AP test has the right to use both. They prefer arc sine too, because they don't want you doing this dumb mistake. Now, if you know enough trig to be doing this lesson, you can all tell me what function this is. What function is 1 over sine? If you said or thought cosecant x, you are correct. Congratulations. These other arc functions are the same. They're just the inverse functions of this, of cosine or tangent. What this is showing is that when I put x in, I'm getting out y. That means cosine of y equals x. It is basically telling you that arc cosine is undoing cosine, or that cosine is undoing arc cosine. It's the connection between natural log and e, between squaring and square rooting, between, I don't know, adding to and subtracting to. These are the domains of each of these functions. Yes, you need to know them. The domains here, we're thinking that these domains are the trig ratios that come out when you plug an angle in. So these domains are the outputs of sine and cosine and tangent, and now they're the inputs of arc cosine, arc sine, and arc tangent. So the ranges, in a corresponding way, were angles, were the inputs of sine, cosine, and tangent, and so they're the outputs of arc sine, arc cosine, and arc tangent. Now, Francis, I'm talking to you personally. This is why arctan is the most beautiful function. Obviously, arctan is the only one with a domain of all real numbers. And if you don't understand, these are all interval notations, and that this is shorthand for all reals. It's the only one with those two. It has a nice range. It is an open range. It has two horizontal asymptotes. You'll see it in a second. These other ones have weird ranges. Notice again, all of these ranges are in pi. All of these ranges are in radians, because radians is the only thing we're using in calculus. Again, if you do not understand which angle is pi over 2, or which angle it corresponds to pi in degrees, you are not ready to watch this. Wait. Now, if you said or thought that the angle for pi over 2 is 90 degrees, and the angle for pi is 180 degrees, you are correct. Let us continue. So we're going to graph each indicated inverse trig functions. Do you have to memorize this? Would be the most common question. Yes, probably. These are graphs you should know, because these graphs tell you the range and the domain. If you have the graph, you know the range, you know the domain. If you want to just memorize the range and domain, you can probably figure it out just by plugging points in. The idea is, at 1, at an x value of 1, what angle in sine gives me an output of 1? If you said or thought pi over 2, you are correct. Sine of 0 was 0, and sine of negative pi over 2 was negative 1. Now, it looks linear. It's not. It looks kind of like this, which is kind of like a tangent looking thing, except it has endpoints. Notice the dots. Do not draw arrows, ever. Arc cosine. When cosine is 0, cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1. That looks off. Negative 1. Whatever. Again, not a line, but a curve. Oh, gosh. Obviously, they should touch. One more try. Perfect. At least good enough for me. It should hit that point. It hits that point. Pretend it hits that point. That's the y-intercept. That's the y-intercept. If you have no idea what I mean when I say cosine of pi is negative 1, you are not ready for this lesson. Wait until you learn trig in AB, or don't take the BC test. Alright. Arctan. Get ready. Hold your seats. Buckle up, buckaroos. I'm going to switch the colors just because it's so special. Arctan. Tan of 0 is 0. And now you try to do it the other way. Tan of pi over 2 doesn't exist, is what you should have said in your mind if you're ready for this lesson. Tan of pi over 4 is 1. Tan of pi over 2 doesn't exist. The tan function has a vertical asymptote, so the arctan function has a horizontal asymptote. The tan function has a vertical asymptote at the x value pi over 2 and negative pi over 2, so the arctan function will have a horizontal asymptote at pi over 2 and negative pi over 2. Bump, 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 bump. So it will look like this. Something close to that. It looks more pretty in real life, but your teacher can't draw. So here we go. One more time. Do it for arctan. That really should be around pi over 4. I'm going to write that point just so you guys don't get confused. 1 comma pi over 4. -1, negative pi over 4. It's smooth. It's beautiful. It's defined everywhere. It's the best. Bar none. Now, to help you remember these domains, we had this picture. We have this picture at play. Arcsine and arctan live here. They live between, they have outputs between pi over 2 and negative pi over 2. Or for arcsine, they have outputs between, I'm sorry, I said that wrong. Arctan has outputs between pi over 2 and negative pi over 2. I was right. Arcsine has outputs between pi over 2 and negative pi over 2. Arccosine has outputs between 0 and pi. So when you're solving equations with these functions, you can only have solutions that follow in these ranges. Okay? Evaluate without a calculator. Yes, you should be able to punch the buttons in and realize what these are saying enough to plug it in the calculator. But you also need to be able to do these by hand. So let's continue. Arctan of 1. You're thinking, what angle, when put into tan, would output 1? And the correct angle is pi over 4. Now I say again, if you said 45 degrees, yeah, you are sort of right, but you will be marked wrong every time. It needs to be pi over 4. I say again, if you were smarter, the smartest people in here might be like, oh wait, aren't there infinitely many solutions? Sure, pi over 4, but what about 9 pi over 4, Mr. Leven? I say again, look, arctan only lives here. Arctan can't give you 9 pi over 4. We're only going between negative pi over 2 and positive pi over 2. There's only one value between negative pi over 2 and positive pi over 2 that gives you pi over 4, and it's, that gives you 1, and it's pi over 4. Blah. Cosine inverse of -1. Cosine inverse of -1. We have... Sorry, there's someone at the door, and they're being kind of annoying. Cosine inverse of -1. What angle, when you plug into cosine, would give you -1? The only correct answer between 0 and pi is pi. Now, I don't mean 0 and pi are my only option. I mean of every angle between 0 and pi. The interval 0 to pi. Sine inverse of √3 over 2. And now we might finally be testing your trig knowledge. We finally might be testing your trig knowledge that you should know what angle in sine would output √3 over 2. So if you haven't mastered trig yet, a helpful picture, √3 is only ever coming from a very special right triangle, a 30, 60, 90 right triangle. And why are we calling it a 30, 60, 90 right triangle? I don't know. That's lost in time. So here's the angle. Sine is opposite over hypotenuse. Which angle would live inside this special right triangle? Well, that angle would be pi over 3. But this is not the right triangle. It's upside down. Because it was negative root 3. Okay? So instead of pi over 3, it's negative pi over 3. Oh my gosh, that pi was kind of ugly. Sorry. Arc sine of 2. If you got the pattern right so far, it's asking which angle in sine would output a value of 2. Are you thinking about it? Are you racking your cabeza? Well, the only option is does not exist. There are no values of theta. There are no angles into which sine can put out a number greater than 1. Sine's range, recall, is between negative 1 and 1. That's why arc sine's domain is between negative 1 and 1. So this question doesn't make sense. It's not defined there. Solve for x. Alright. So the thing I want to do here, just like how if it was log of x squared minus 3, what would you do? As much as you don't want to, what would you do to get rid of log? If you said or thought I would make both sides an exponent of e, that's right. Because e and log are inverse functions. What's the inverse function of arc sine? I'll give you 3 guesses. Good, it's sine. Nice job, everybody. If you didn't get that right, we got a problem. Because that's literally been the only purpose of this lecture so far. And whatever I do to one side, I better do it to the other. Yeah? Yeah. Alright. Sine and arc sine cancel out. Just like e and natural log. Just like, again, root 2 and... Oh, God, not root 2. Oh, my God. That's what you all think. Squaring and square root cancel out. Log and e cancel out. Sine and arc sine cancel out. We're left with x squared minus 3. And sine of pi over 2. Another chance to test yourself. Do I know trig? It's 1. And now we solve. Plus 3. Plus 3. See, I'm going to write this out. You might be watching this after you bombed another test because you don't know your algebra. I didn't write it the square root. I don't know, that's surprising. Here, bam. I square rooted both sides. And when you create the square root, make sure you add the plus or minus. That's why there's a plus or minus 2. Now, children, kiddos, people, gente, make sure both of these solutions work. Where does positive 2 work? Positive 2 squared. 4 minus 3, 1. Is arc sine of 1 pi over 2? Yes. Negative 2 squared. Positive 4. Positive 4 minus 3, 1. Arc sine of 1 pi over 2. Check, check, check. Sketch a right triangle and evaluate without a calculator. I got this. I love right triangles. That's how I do my trig. If you haven't seen me teach trig yet, I'm not a big unit circle person. That's just a personal thing. I'm probably not as fast as people who've memorized the unit circle. I always will say that. But boy, do I love my right triangles. Shapes are great. Now, find tan of x given that x equals arc cosine of 2 root 5. So when they mean sketch a right triangle, here I go. So, that's a pretty straight line. I'm pretty proud of that. What goes in here is the ratio. So what comes out of arc cosine, the things that come out of arc cosine are angles. Angles are coming out of arc cosine. So where is x? X is an angle. X is right there. Now why did I draw my triangle like this? Arc cosine. Then go back to cosine. Cosine is what over what? Adjacent over hypotenuse. Could you have put x anywhere you wanted? Yeah, not the right angle, obviously. It would have flipped things around, but it's fine. I like doing it this way. Positive 2, root 5, root 5. Adjacent over hypotenuse. Ka, so katoa. Now you need to know what this side is because tan x is opposite over adjacent. So I need to find this side. Well, there's a special relationship that relates the sides of a right triangle. Pythagorean theorem. Boy, I can't even tell you guys. I cannot even tell you how much time I spend on the weekend talking to this kid about Pythagorean theorem. Now, lest you think I'm just running around the library finding strange children to teach about Pythagorean theorem, I assure you, it's not that way at all. I'm finding normal children who hire me to tutor them, and I teach them about Pythagorean theorem. Plus or minus 1? What do we think, guys? Could it be minus 1? No, it has to be plus 1. Why does it have to be plus 1? Because of where arc cosine lives. If this was negative 1, this triangle would flip down here into the no-no zone for arc cosine. So, overall, tan x opposite over adjacent. Dunzo. One more time, since it's the first time I'm doing this, or maybe the first video you're watching. If, like right now I would say to the class, are there any questions about anything I've said? And maybe someone would say something. One of like 2 people in your class would be like, oh, here's a question. So, if you have questions, you need to come ask me. You need to come track me down. If I'm still alive when you're watching this video, I'm probably still going to school and being there until like 6:30 p.m. That's just me. Find cosine y, given that y equals arc sine x. Huh. That seems like a strange question, Mr. Leven, but whatever. I'll do it. So, again, we're talking about a right triangle. Y is going into cosine. Y is coming out of arc sine. Y must be the angle. Arc sine is x. Arc sine is opposite over hypotenuse, or related to it, over 1. X is opposite the angle. 1 is the hypotenuse. So what is this side? What is this base side down here? We use Pythagorean theorem again. 1 squared equals x squared plus unknown. Oh, I would use x and y. Let's go crazy and call it z. One minus x squared, because 1 squared is 1. I'm trying to solve for z. Z equals positive root 1 minus x squared. Why not negative root? Why not the negative root? Because then z would be this way, and then we'd be out of the range for arc sine. Now that's not the most important thing. What's important is that we're proving that cosine of y adjacent over hypotenuse would be adjacent over hypotenuse. Now David's doing something funny. 1 minus x squared over 1. I could simplify that, obviously. 1 minus x squared, like that. Ta-da! Ta-da! Use your answer from example 5 to find d by dx of arcsine. Donde notation mean? The notation means find the derivative of arcsine. Well, let us assume, children, in our infinite wisdom, that y is arcsine of x. Now, if your first instinct is to differentiate both sides, I applaud you. But the problem is we don't know how to take the derivative of arcsine. That's the whole idea, guys. So instead, sine of both sides. Undo arcsine. Sine y, sine, equals x. Is this something I know how to differentiate? Boy, I sure do. I love differentiating sine. Again, if you're about to say, oh my god, I don't know what the derivative of sine is, you either need to pause this lesson, go through the BC book, pull out your memorization sheet, or, I don't know, figure things out. The derivative of sine, you must know. You must know that the derivative of sine is... I'm going to catch my slides up with my brain while you're all scrambling to get your notes out. Oh, there was that memorization sheet Mr. Leven told us to print out? Wow. Derivative of sine is cosine y. Now, we're differentiating with respect to x, so you must remember the chain rule. Bum, bum, bum. dA by dx, derivative of x is 1. No chain rule, because it's just x. Y prime equals 1 over cozy. And we just found out cozy, like it's right above for you guys, if you printed out the notes, which I hope you did. 1 over the square root 1 minus x squared. Beautiful. What a great formula. It's not as cool as arctan. Hold your horses, guys. Don't get excited. It's not as cool as arctan. Now, you may have seen this somewhere. Where may you have seen this? In that memorization sheet you just pulled out, where it tells you to memorize all the values of this and that and the other thing. Now we're coming up on a half hour. We're only halfway through. I might pause it. There's really not that much more. You might want to pause it after we do derivatives. I think I'll just continue so it's all in one place. You might want to pause it, do the derivatives, do some derivative problems, and then come back and do some integral problems later. It depends on your schedule. It depends on how much of what's made sense so far. Now, here I go with this box again. This box is frustrating me because I think some of you don't understand still, to this day, that the chain rule problems are the only type of problems you need. Now that's pretty funny. The chain rule problems are the only type of problems you need. These are all the same. These only work when it's just x. Why do you teach us? Because sometimes it is just x. And then you shouldn't have to think about the derivatives. These are all you need, though. These are what I memorize. You always have that hook on. Multiplied in, put it on the top, whatever. Arc sine of u. Arc sine of u. 1 over 1 minus u squared inside the square root. Okay? Just like that. That u matches that u. That u matches that u. That u matches that u. Just to be clear, crystal clear. Those on the top are not the same. It's the derivative. To get out of arc sine, we do 1 over 1 minus u squared. And then I multiply by the derivative of whatever was inside sine. Arc sine. Now you'll see more of this in a second when we do the actual examples. But make sure this makes sense. Like, not that you could prove it if I asked you to, although you should be able to, but that you could do a derivative problem, maybe even now. And also, let's take a second to appreciate arctan. You see what I'm saying? You see what I'm saying, people? Beautiful function. No square root in the bottom. 1 plus. Oh, it's a thing of beauty. That's why, Francis. That's why it makes grown men weep tears of joy. Alright, guys. Here we go. So the first thing I notice is that this says arctan. So I'm going to use the arctan rule, not the arc cosine, not the arc sine rule. Interesting. Spicy. Muy caliente. 2y minus y. 2y minus y. So that's the inside part. So what I'm going to do here, differentiating both sides, g prime of y equals, it's always fractions. That's why we're doing it, guys. There's going to be a lot of fraction integrals, and that's what makes BC harder, is AB only has to worry about log and these two, the ones we were talking about today. AB has to worry about those two, logs and these kinds. BC has to worry about this and lots of other kinds of fraction integrals. There are lots of different varieties, lots of different techniques of integration to learn. But it all falls under the integration umbrella. Here we go. 1 plus squared. And what goes in the plus is that inside right there. Next one. Ta-da! On top, I differentiate this. And if you cannot quickly differentiate that, you might not be eligible for the BC. You might not be able to do it. 2y minus 1, differentiating with respect to y, because this is a function of y, 2. And again, if you're mystified by that, you might not be in the right spot. You might not want to take the BC test. F of x equals arc sine. Arc sine, so I'm going to use the arc sine rule. F prime of x equals square root 1 minus blah squared. And what's blah? The inside of arc sine. But bam. So it's square root x. And on top, I told you guys, memorize the square root of x. the derivative of the square root of x should look like this. Pretty much instantly. If you thought this class wouldn't be a lot of memorization, I am sorry to tell you that you are not right. This class has memorization, just mathematical kind, symbolic. Somewhat harder than history because, you know, in history at least, you know, names, places, people, years, all things you're familiar with. Here it's just letters and symbols. F prime. You should be able to simplify this. If what I do right now does not make sense to you, again, you might not be ready for the BC test. Just take the AB test. It's okay. You won't disappoint me. Some people in here aren't ready. Some people in here are challenging themselves. I like that. I want you to challenge yourself. But I don't want you to challenge yourself and then not do well. Make sure your algebra is on point. Make sure you understand why this is the correct simplification. Not anything else. Okay? If you have a high A, you should have been able to do that pretty quickly. Pretty quickly. Don't worry if you can't do it flawless like me on the first time. But you should be able to do it. Alright, here we go. First thing I notice, our cosine. Oh, Mr. Levin's giving you all different types. Wow, what a surprise. H prime of t. Oh, forgot the prime. I don't know, maybe you saw it or not, but did it not write? Did I not write it? Who knows? Oh, sorry. Try that line one more time. Third time's a charm. Fourth time's a charm. Okay. Our cosine, square root 1 minus parentheses of something squared. And on top, I have a little negative because it's our cosine. Go back. It's like an inch above where you're writing. Look at the rule for our cosine. There's a negative. What goes down here? The current inside. Natural log t. What goes up here? The derivative of natural log t. What's the derivative of natural log t? Again, if you haven't memorized this yet, you have a problem. 1 over t. Done. Boom. Next. Interesting one. Very, very, very interesting. For a very, very varied number of reasons. Very, very varied. Wow. Okay, here we go. It's an arc sine. dy dx equals fraction bar square root 1 minus the current inside squared. Who is the current inside? It's x over 2. I really did a good job highlighting that. Bam. And now, what's the derivative of the current inside? The derivative of the current inside is 1 over 2. Ah. Now it says this funny word, this funny jumble of symbols that aren't math. They look like a bunch of variables multiplied together. S times I times M. Uh-oh. I think it's a word. It says simplify. As you know, if it says simplify, you have to simplify it. Let's do it. So just like before, when I'm dividing two fractions, the bottom goes on the bottom. This is part of that. 1 over 2. Oh, that was a pretty straight line. Why can't I always do it that way? 1 minus x over 4. See how I squared that? I didn't square that. X squared over 4. Oh, gosh. See, I just lectured you guys on it, and now I messed that up. Now, some of you might know, I can pull numbers outside the square root, inside the square root, by squaring them. That this is the same as this. Done. I distributed. I don't think I said that. I distributed it. So that's interesting. It's interesting for a variety of reasons. You will see why in a second. You will see why that is an important example for what we're about to do. It means that things that look like this have an antiderivative like this. That's an important relationship. Regardless of how simple this looks, its antiderivative is even simpler. Right? Its derivative is this, after some algebraic manipulation. And in general, you should be worried about that. If you see this guy inside an integral, as always, I'm looking for patterns. There's a natural log t, there's a took-off. Let me try to replace it. There's a root x, there's a took-off. There's a 2y minus 1, there's a took-off.